This is the Phantom Premium 3.0 6DOF haptic arm. It features 6 degrees of motion sensing and force feedback over a range of motion comparable to that of the human arm. Visible here are 2 of the 3 base motors and optical encoders responsible for reporting the arm's position. The third encoder and motor assembly is here on the base of the arm near the Phantom's data cables. The arm itself is made of 4 segments and features 3 additional gimbal motors which apply torque here at the handle. The Phantom arm in turn connects to a control box which houses the power supply, motor amplifiers, and control logic. This interior view of the control box reveals the Copley Controls Model 645 power supply in red and 6 Copley Controls Model 306A motor amplifiers in blue. This is the Phantom harness board assembly, which houses the Phantom's input-output connectors and control logic. The 37-pin D-sub connector carries information to and from the host PC. The 15-pin D-sub connector carries data from the optical encoders to the board. These 2 20-pin connectors carry motor control signals and motor status signals. Each connector is split into 3 blocks of 6 pins each, with each block responsible for a single motor. Finally, the 2 10-pin connectors are used for auxiliary functions of the Phantom control box. One is responsible for controlling the box's LED status lights, while the other handles the emergency kill switch, amplifier fuse reset, and distribution of power from the power supply to the board. Over the course of this project, we were unable to implement motor control due to the unknown and complicated interaction of the 4 ICs which control the motor's enable signals. We were able to activate all 6 motors by directly interfacing with the motor amplifiers, but this technique does not give us the fine control necessary for a quality haptic experience. However, we were able to read data out of the Phantom's optical encoders and visualize it both on an oscilloscope and on a PC via an Arduino Mega 2560. Here you can see that the width of the output pulses depends on the speed of rotation. A slow, constant motion produces wide pulses, while rapid movements produce narrow, high-frequency pulses. Unfortunately, we were unable to develop a fully functioning device driver due to time constraints. Our work has revealed much information about the Phantom's previously unknown black box control scheme, and provides a solid foundation for future development using the Phantom Premium 3.0 6DOF.